On the night of October 10th, 2025, the Hubble Space Telescope recorded something it wasn't supposed to see. A jet thin, brilliant and impossibly violent erupted from a faint speck in the constellation of Pisces. It wasn't just outgassing, it was a torrent, a stream of vaporized water flung into space with the fury of a ruptured pressure line, a fire hose, in the dark. Within minutes, that jet began to twist sunlight into a halo of shifting brightness, as though the object itself were breathing against the vacuum. Across the network, astronomers' monitors lit up with the same anomaly. The radiation pressure from the sun wasn't enough to explain what they were seeing. The equations didn't close. The trajectory data refused to fit. And then, just 3 days later, new images from the Catalina Sky Survey revealed a ghostly line extending in the wrong direction, an anti-tail, a reversed plume of dust pointing toward the sun instead of away from it. Such a sight had never been so clearly documented in an interstellar visitor before. In observatories across the world, analysts leaned closer to their screens, checking timestamps, recalculating vectors, trying to decide whether this was a trick of geometry or the first real evidence of a force we had not yet modeled. Something was bending the rules. The question was, what? Tonight, we embark on a new journey where the theme of 3I Atlas meets Mars gravity, the unmodeled case, appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you learn, focus, or simply relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. Now, as data, streams from the trace gas orbiter near Mars begin to show minute flickers, unmodeled residuals in the spacecraft's tracking field. The mystery takes on a new layer. Did Mars itself tug subtly on the interstellar visitor, altering its course? Or is there something deeper, an invisible thrust born from jets of vapor, challenging our most trusted models of motion in the solar system? The trajectory of interstellar object 3I Atlas, following its close encounter with Mars in October 2025, has presented a quiet but persistent enigma. According to the ephemeris updated after the 3rd of October, a consistent, minute deviation in its acceleration vector was recorded, a vector that strayed from the predicted path dictated by the gravitational pull of the Sun and the Martian sphere of influence. The navigation teams at the European Space Operations Centre reported residuals in the orbital data that exceeded the expected threshold of background noise. The initial, mainstream scientific explanation points toward a non-gravitational force, a well-documented phenomenon in cometary science where outgassing acts as a natural thruster, subtly altering an object's path. Yet, the timing and nature of this particular anomaly give one pause. Could a simple jet of gas, erupting from a hidden fissure in a presumed icy core, account for such a precise and measured deflection, as if a second, unseen hand had gently tugged at the object's course? The data from other Martian orbiters adds a layer of compelling context. The Trace Gas Orbiter and the veteran Mars Express concurrently registered a transient increase in local plasma activity and atmospheric excitation. Simultaneously, the Minor Planet Center processed photometric data from the Subaru and Very Large telescopes, confirming a slight but detectable intensification of a coma around 3I Atlas. This confluence of evidence strongly supports the outgassing hypothesis. We can posit a level 1 interpretation, an eccentric vent of volatile material, perhaps carbon monoxide or carbon dioxide ices, sublimating in the weak sunlight, provided a short-lived, non-gravitational acceleration. But this merely opens the door to deeper mysteries. What if this outgassing was not a single event, but a structured process? A level 2 hypothesis suggests that, As the object rotates, this jet acts like a fan, pushing the trajectory not in a smooth curve, but in a subtle, saw-toothed path. And if the object's rotation state is chaotic, a level 3 scenario emerges, where the thrust vector varies wildly, creating a noisy signal that merely mimics the signature of a gravitational pull. Is the tug we observe merely the stochastic sputtering of a dying comet, or could it be the signature of something far more structured? This leads us to the more speculative frontier. Perhaps the outgassing itself is not from a natural reservoir. One bold hypothesis proposes that the object's core is not a solid mass, but a porous, pumice-like structure, a microgravity field of its own, where trapped ices create a comet lighter than its weight, and the resulting jet is a directed, almost engineered, release. Another considers the possibility of an electrically charged dust envelope interacting with the Martian plasma torus, a complex electromagnetic dance imparting momentum. If the outgassing jet is the dominant force, this encounter presents a monumental opportunity to recalibrate our models of non-gravitational forces for all interstellar objects, paving the way for better predictions, for encountering or perhaps one day intercepting the next celestial traveler. But if the cause is not so simple, what fundamental mechanics are we yet to comprehend? The implications of this subtle tug extend far beyond the object itself, forcing a recalibration of our own instruments and expectations. As the trace gas orbiter continued its mission, its continuous imaging sequences began to reveal their own curiosities, not in the object itself, but at the very edges of the frame. The resulting animated data, a silent film of the Martian expanse, showed faint, unaccounted-for glimmers, minute shifts in the stellar background that should have been static. These were not the grand discoveries of new moons or asteroids, but something far more insidious, a faint signature of error. The researchers at the European Space Agency found themselves engaged in a meticulous, silent battle with their own data, forced to constantly adjust positioning parameters to compensate for these unmodeled residuals. The very tools we use to map the heavens were reporting a sky that was subtly, inexplicably, in flux. What unseen influence was bending the light, or the perception of it, around Mars? This was no longer just about the path of a distant visitor, but about the stability of our own celestial coordinate system in its vicinity. The gifts from the trace gas orbiter, those looping animations meant to confirm a stable orbit, had instead become a puzzle box. Each frame contained a ghost of a discrepancy, a slight brightness deviation at the rim of the field of view that standard models of orbital mechanics and instrumental error could not erase. This forced the navigation teams to embark on a new painstaking phase of analysis, sifting through these unmodeled residuals not as noise, but as a potential signal. Were these faint glimmers merely a testament to the immense difficulty of precise celestial navigation from 100 million kilometers away, or were they the faint echoes of the same phenomenon that had tugged at 3I Atlas, a distortion that was now affecting our very own eyes in the sky? The quest to understand the object's path had inadvertently revealed a distortion in our own. The Star Tracker camera, a silent sentinel aboard the trace gas orbiter, is engineered to perceive the cosmos as a fixed and predictable tapestry. Its purpose is to lock onto the immutable positions of distant suns, using their light to maintain the spacecraft's precise orientation in the void. Yet, in the first week of October 2025, its steady gaze was broken. A sequence of images, compiled into a trembling GIF, revealed a persistent, subtle shudder at the very edge of its field of view. This was not a catastrophic failure, but a whisper of anomaly, a deviation so slight it would have been dismissed as sensor noise just a decade prior. But for the flight dynamics team at ESOC, this digital tremor forced a complete recalibration of their celestial matrix, a delicate rebalancing of the galactic scales upon which the orbiter's navigation depends. How could a flicker at the periphery of a single instrument's vision demand such a fundamental recalibration of our certainty? The immediate conventional explanation pointed to the mundane environment of space itself. The spacecraft was orbiting Mars, a planet whose tenuous exosphere and dust-filled environment are known to host microscopic, charged particles. According to current models, a single, highly charged dust grain drifting into the precise focal plane of the star tracker could create a minute but persistent optical illusion. Its electric field might subtly distort the incoming starlight, bending it just enough to fool the sensitive optics into registering a shift in the cosmic background. This would be a known, if rare, hazard of interplanetary travel, a ghost in the machine born of simple physics. But does this simple explanation truly account for the specific, patterned nature of the tremor, a deviation that seemed to pulse with a rhythm all its own? This leads us to a more speculative hypothesis. The timing of this anomaly coincided precisely with the close approach of the interstellar object designated 3I Atlas. What if the object itself was the source of the deception? We must consider the possibility that 3I Atlas was not a simple, inert rock. Perhaps the surface, rotating under the weak sunlight, possessed facets of highly reflective ice or mineral that acted as a transient mirror. As it spun, these facets could have flashed pulses of modulated light towards the orbiter, creating a phantom signal at the edge of the star tracker's vision, a stellar illusion choreographed by the object's rotation. The instrument would not be broken, but rather bewitched by a light echo from a passing wanderer. Could an object from another star system be capable of such complex, albeit unintentional, communication? Pushing the speculation further, we must entertain an even more profound possibility rooted in the very fabric of space-time. The general theory of relativity tells us that mass bends light, and this effect is not limited to stars and galaxies. A sufficiently dense concentration of mass, such as a large, pre-planetary dust grain within the Martian system, could act as a microgravitational lens. This lensing effect would be infinitesimal, yet for an instrument as sensitive as the star tracker, potentially detectable. It would create a transient warping of the starlight, a shimmer that moves as the lensing mass moves. The unmodeled residuals in the navigation data, flagged for later analysis, could be the faint signature of this subtle cosmic curvature. Are we, for the first time, detecting the ghostly fingerprints of microscopic gravity wells, distorting our view of the heavens? The forensic analysis of this event proceeded with meticulous care. The initial corrective action, Level 1, was a standard 0-point adjustment in the software, a digital nudge that stabilized the image and restored nominal operations. This simple fix also revealed a slight corresponding shift in the calculated orbital path of 3I Atlas itself. Level 2 analysis, however, uncovered something far more intriguing. The jitter was not random. It contained a pattern, a faint periodic signal that correlated directly with the estimated rotation period of the interstellar object. This was no longer a simple case of instrument error. It was a dialogue, however one-sided, with the visitor. And at Level 3, the most profound insight emerged. By focusing not on the stable stars at the center, but on the shuddering ones at the edge of the field of view, scientists unlocked a rare background signal. It revealed an orbital dust density around Mars that was orders of magnitude higher than any previous model had predicted, a shroud of primordial material previously invisible to our instruments. What other secrets are hidden, not in the clear light of the stars, but in the trembling shadows at the margins of our perception? The ultimate legacy of this event was not merely a solved anomaly, but the birth of a new protocol. The hard-won experience of recalibrating the galaxy in real time was codified into a tactical handbook for all future planetary orbital observations. It laid the foundational principles for what may one day become a fully realized interplanetary sentry network, a system designed not just to see, but to interpret the faintest tremors in the cosmic web. This incident proved that our spacecraft are not merely passive observers, but can become active participants in a new form of celestial forensics. Yet, this meticulous recalibration was merely the prelude, a necessary step to prepare our instruments for the main event, for the unmodeled scenario that was already unfolding as 3I Atlas made its fateful close approach to the red planet. On the 3rd of October, 2025, the trajectory of the interstellar object designated 3I Atlas intersected the orbit of Mars. It was a calculated near miss, an event predicted by the meticulous choreography of orbital mechanics, governed by the Keplerian laws and refined by complex N-body simulations. Yet, as the data streams converged from tracking stations across Earth and from orbiters around the red planet, a subtle but persistent anomaly emerged. The object passed marginally closer than every model had forecast. This was not a catastrophic failure of prediction, but a whisper of discrepancy, a deviation measured in mere hundreds of kilometers, a distance cosmically insignificant, yet scientifically profound. It was the opening act of what would become known in the internal logs as the unmodeled case. If our models of the solar system are so precise, how could such a small, unaccounted-for variance occur at such a critical moment? The immediate, mainstream scientific explanation points to the imperfections inherent in our modeling of planetary gravity. Mars is not a perfect, homogeneous sphere. Its oblate shape and the uneven density of its interior create a gravitational field with subtle complexities. This is quantified by a parameter known as J2, the second dynamic form factor. According to current models, the value used for Mars's J2 in the preliminary trajectory simulations may have been an oversimplification, a smoothed-over average that failed to capture a local gravitational nuance. A slight adjustment to this parameter could, in theory, resolve the discrepancy, bringing the predicted flyby distance perfectly in line with the observed one. It would be a testament to the iterative process of science, where each anomaly merely refines our existing understanding. But what if the gravitational field of Mars is not the variable in this equation? What if the variable was the object itself? This introduces our first speculative hypothesis. Perhaps the core of 3I Atlas is not a simple, monolithic rock. It may harbor volatile ices, not of water, but of carbon monoxide and carbon dioxide, preserved in the deep freeze of interstellar space for millions of years. As the object made its close approach to Mars, the increasing solar radiation could have triggered a sudden, localized outburst of sublimation, a jet of gas acting as a natural thruster, imparting a tiny but measurable non-gravitational force. Data from the European Space Agency's Trace Gas Orbiter, or TGO, recorded a slight deviation from the purely gravitational Kepler plus N body predictions. Meanwhile, observatories on Earth, including Lowell and the global network of Las Cumbres, documented a faint but detectable increase in the object's brightness, on the order of 0.1 to 0.2 magnitudes in the 24 hours surrounding its closest approach. This brightening is consistent with the sudden release of reflective gas and dust. Could a pocket of ancient alien ice, waking from its eons-long slumber, have gently nudged this traveler from its calculated path? There exists a yet more intricate possibility, a second layer of speculation that challenges our understanding of material integrity. The gravitational forces during a close planetary passage are not uniform. They create a tidal stress, stretching and compressing the passing body. For a robust asteroid, this effect is negligible. But for a fractal-like porous aggregate, a relic from the formation of an alien solar system, these microtidal forces could be catastrophic on a miniature scale. The immense gradient between the point closest to Mars and the point farthest away might have induced microscopic fracturing at the precise moment of periapsis. This would not be a spectacular disintegration, but a silent, structural failure, a network of cracks propagating through its nucleus, potentially releasing trapped volatiles and altering its trajectory through a combination of outgassing and a minute change in its mass distribution. The Jet Propulsion Laboratory's Horizons system, the definitive database for solar system dynamics, was updated to reflect the new orbit of 3I Atlas, noting an increased dispersion in the possible future paths. Was this dispersion not just a measure of uncertainty, but a fingerprint of an object whose very structure was compromised by its encounter? Thus, we are left with a cascade of hypotheses, each ascending in its implications. The first level is a simple correction, a missing gravitational parameter, easily remedied with more data. The second level introduces a transient, non-gravitational force, requiring a new term in the Minor Planet Center's cataloging protocols to describe its motion. But the third and most profound level suggests we are witnessing a new class of physics, governing objects in the close-in regions of planetary influence. It posits that interstellar interlopers, forged in unknown environments, may respond to stresses in ways our own native asteroids do not. Their fundamental material properties could exist outside our current taxonomy. Does the unmodeled case therefore reveal less about 3I Atlas and more about the limitations of our own scientific categories? The true outcome of this encounter is not merely a revised set of orbital elements. It has become a rigorous test for the scientific mindset itself. It demands that we sit with the discomfort of uncertainty, then systematically deconstruct the event, peeling back layer after layer to evolve our models of not just how objects move, but what they are. This process of iterative revelation, of building a more nuanced understanding of interstellar flight through anomaly, is the lasting legacy of that October flyby. But if the object's path was subtly altered, what of its very substance? Did the closed passage leave more than just a gravitational puzzle in its wake? The answer may lie not in the silent void it traversed, but in the faint, spectral whispers it cast upon the instruments watching from Mars' orbit. The faint spectral whispers captured by the Trace Gas Orbiter and Mars Express in early October 2025 present a paradox of absence. The data is there, a spectral signature of profound implication, yet it is so whisper-quiet that it carves out a void in our understanding, precisely at the most critical moment of observation. Instruments of unparalleled sensitivity, the Omega and SpyCam spectrometers aboard Mars Express, and the Nomad suite on the Trace Gas Orbiter all registered a signal, but one with a signal-to-noise ratio so perilously low it resides on the very frontier of detectability. Specific absorption bands, particularly around 3 micrometers and 1.4 micrometers, associated with water and other volatiles, showed a curious weakness, a spectral signature that was less a declaration and more a hesitant murmur. Concurrent observations from ground-based giants like the ESO's Cryas Plus instrument sought the telltale sign of methane, only to report values persistently below the threshold of confirmation. We have a detection that is, in essence, a structured absence, a ghost in the machine of spectral analysis. What does it mean when our most advanced instruments report not on what is seen, but on the faint, structured echo of what might be missing? The mainstream scientific explanation points first to the unforgiving physics of observation. According to current models, the extreme obliquity of the object's approach and its high rotational state could have created a highly unfavorable illumination geometry. The sun may have been glancing off the surface at such a shallow angle that the reflected light, carrying its encoded spectral information, was simply too faint for our instruments to capture with high fidelity. Furthermore, the object's small size and potentially very low albedo would compound this effect, rendering it an exceptionally challenging target. The weak water absorption lines, when compared to the expected cometary coma profile, could simply indicate a body that is far less active than typical comets. A largely inert interplanetary vagabond whose volatile ices are deeply sequestered beneath a barren crust. This is the conservative, the most probable interpretation, a confluence of difficult observational circumstances giving rise to an ambiguous, noisy dataset. But does a simple lack of light truly account for the specific, structured nature of this spectral silence, for the way certain bands seem to fade with a curious selectivity? This leads us to a more speculative first hypothesis, that we are not looking at a bare surface, but one deliberately, or naturally, obscured. Imagine a mantle not of coarse regolith, but of nanoscale dust particles, a fine, electrostatically charged dust shroud clinging to the surface. Such a layer, with grain sizes on the order of the wavelength of light itself, would not simply block reflection, it would scatter it, diffuse it, acting as a form of anti-reflective coating on a cosmic scale. This nanodust cloak could effectively mask the underlying spectral features of ices like ammonia or water, smearing their sharp absorption lines into the background noise. It would be a perfect camouflage, not against our telescopes, but against our spectrometers, the very tools we use to discern composition. Is it possible that this object wears a veil, a shroud of its own making, tailored to evade our most penetrating analytical gaze? Yet, the mystery deepens with a second, more dynamic hypothesis. What if the very act of its close encounter with the Sun, even at the distance of Mars, initiated a transient and transformative process? The object's surface, bombarded by solar ultraviolet radiation, could have generated a faint but pervasive ion halo, a thin envelope of charged particles. This plasma sheath, while not dense enough to form a visible coma, could interact with incoming starlight in subtle ways, perhaps through resonant scattering or induced polarization effects that preferentially weaken specific absorption lines, like those of water. The spectral signature would not be erased, but selectively washed out, as if the light itself was being filtered through a tenuous, energetic lens. Could the object's own interaction with the stellar wind create a temporary, shimmering barrier that obscures its true, chemical nature from our view? Pushing the speculation further, a third hypothesis emerges from the realm of complex and rapid surface chemistry. The data from the 2nd to the 4th of October shows not just a weak signal, but a signal that appears to be in a state of flux. The spectral lines seem to slip in and out of our observational windows. This could be the signature of an object with a hyper-evolutionary surface. Imagine a crust rich in simple organic compounds, subjected to intense and fluctuating ultraviolet radiation. This could drive rapid, localized polymerization, creating a thin, transient layer of complex organic polymers. This film would have its own, ever-changing spectral properties. As it forms and dissipates on timescales of minutes or seconds, its absorption features would overlap and interfere with the underlying ices, creating a spectral profile that is inherently unstable and maddeningly difficult to pin down. The data gap, then, is not just a product of low light, but of a surface chemistry operating at a speed we are scarcely equipped to measure. Are we witnessing not a static world, but a chameleonic one, its identity shifting faster than our instruments can capture? The immediate consequence of this profound data gap is a fundamental shift in our approach to future exploration. The encounter has exposed a critical blind spot in our astronomical toolkit. We are optimized for observing the bright and the obvious, not the faint and the evasive. This has catalyzed the design philosophy for a new generation of sensors, instruments specifically engineered to look at the edge. These would be hypersensitive detectors capable of not only gathering more photons, but of analyzing the polarization state of light, of searching for spectral anomalies in the noise itself, and of making rapid, high-cadence observations to catch fleeting chemical transitions. The goal is to create a suite of instruments that treats noise not as an enemy to be eliminated, but as a landscape to be meticulously surveyed. For if this object is a prototype, a herald of other faint visitors from the interstellar deep, then we must learn to see not just the light, but the shadows it casts. How do we build an eye that can perceive an object that does not wish to be seen, or whose very nature is to be perpetually on the verge of invisibility? This spectral enigma, this whisper from the void, inevitably draws our gaze forward, beyond the immediate moment of the encounter. For the true nature of a traveller is not only revealed in its composition, but in its path, in the subtle deviations that speak of forces unseen. As the object, now designated 3I Atlas, receded from Mars after the 3rd of October, its new refined ephemeris was calculated and entered into the catalogues of the solar system. And when this path is laid alongside the historic trajectories of its predecessors, 1I Oumuamua and 2I Borisov, a pattern begins to emerge from the precise mathematics of celestial motion, a pattern that suggests the whisper was merely a prelude to a far more profound anomaly waiting in the silent depths of space. The residuals for the interstellar object, designated 3I Atlas, have, since the 3rd of October, departed from the established script. The plotted points, representing the subtle discrepancies between its observed position and the path predicted by celestial mechanics, have vaulted beyond the quiet, predictable corridors once occupied by its predecessors, 1I Oumuamua and 2I Borisov. This is no minor perturbation, it is a declaration of anomaly. The safe zone, a conceptual boundary defined by the gentle nudge of outgassing seen in comets within our own solar system, has been breached. Where the first two interstellar visitors offered tantalizing but ultimately constrained deviations, 3I Atlas exhibits a dynamic and growing off-track trajectory. What fundamental property, hidden from our immediate view, could propel an object on such a defiant path? Conventional astronomy would first look to the well-understood mechanism of cometary activity. According to current models, as an icy body approaches the Sun, solar heating sublimes subsurface volatiles, creating jets that act as natural thrusters. The resulting non-gravitational forces gently alter the object's orbit, producing the very residuals we track. For 1I Oumuamua, this effect was subtle and debated. For 2I Borisov, it was more pronounced but still fell within the expected envelope of a comet. Scientists suggest the increasing off-track ephemeris of 3I Atlas between the 4th and 9th of October could be due to an exceptionally vigorous, yet still conventional, outgassing event. The object may simply possess a richer reservoir of volatile materials, perhaps carbon monoxide or carbon dioxide, now being violently activated by its solar proximity. But that explanation begins to strain under scrutiny when one examines the historical data. A comparative analysis of the residuals of 1I Oumuamua from 2017 and 2I Borisov from 2019 reveals that the amplitude of 3I Atlas's deviation is not merely stronger, it is of a different character altogether. It is not just the magnitude, but the rate of change that defies a simple cometary analogy. Furthermore, photometric data from the Zwicky Transient Facility and Pan-STARRS networks have recorded a complex light curve with brightness variations that are out of phase with a simple, single-body rotation. This suggests a shape or surface activity that is asymmetrical and dynamic in a way not seen before. Could the standard cometary model, which has served planetary science for centuries, be insufficient to describe the true nature of this traveller from the stars? This leads us to the first speculative hypothesis, that 3I Atlas is not a monolithic chunk of ice and rock, but possesses a structure of an almost ethereal fragility. Imagine a natural aerogel, a fractal, porous matrix of silicate and carbonaceous dust, incredibly lightweight and tenuous. Such a structure would have a low mass, but a very large surface area, making it exquisitely sensitive to radiation pressure and other non-gravitational forces. A gentle push from outgassing, insignificant for a denser body, could impart a significant acceleration to this cosmic sponge. The observed photometric variations, could then be explained by the changing cross-section of this irregular, lacy structure as it tumbles through space. Is it possible we are witnessing not a solid world in miniature, but a delicate skeleton of one, a ghostly assemblage of primordial stardust? Yet, the erratic nature of the residuals hints at a force more complex than a simple, linear thrust. The data implies a torque, a twisting force that cannot be explained by outgassing from a single point. This brings us to a second, more intricate hypothesis: the concept of a binary core, a tango in the void. Perhaps 3I Atlas is not a single object, but a contact binary, or a tightly bound pair, two distinct masses engaged in a complex gravitational dance. Outgassing from the neck between them, or from one component more than the other, would create an imbalanced force. This would not only accelerate the object, but also induce a precession or a chaotic wobble, generating the peculiar off-track motion and the out-of-phase light curve. The object would be steering itself, not with a steady hand, but with a sputtering, unpredictable thruster that constantly changes its orientation. What intricate choreography of mass and force would be required to produce such a perplexing trajectory? And then, there is the engine of this motion to consider. The standard driver of non-gravitational acceleration is the Yarkovsky-O'Keefe-Radzievsky-Paddock, or YORP, effect, where the absorption and re-radiation of sunlight can slowly alter an object's rotation and orbit. For a typical asteroid, this is a gentle, millennial-scale process. But our third hypothesis proposes an amplification of this phenomenon to a dramatic degree. Suppose the surface of 3I Atlas is coated in a layer of ultra-black, superabsorbent carbon dust, a material darker than any we have observed in our solar system. This would maximize the absorption of solar energy. Furthermore, if its structure is the proposed aerogel, the heat would not readily conduct inward, but would be trapped and radiated from the same fine filaments, creating a significantly more powerful and efficient photon thrust. This enhanced YORP effect, working in concert with or even dominating any outgassing forces, could provide the sustained, anomalous push we are witnessing. Have the conditions in another star system conspired to create a solar sail of natural and unprecedented design? We are thus faced with a cascade of analytical interpretations, each level venturing further from the shores of the known. At the first level, we have a simple, if powerful, non-gravitational force of the cometary type. This is the most conservative explanation, requiring only that 3I Atlas is a more active comet than any we have previously catalogued. It is an answer, but one that feels increasingly inadequate as the residuals continue their climb. At the second level of analysis, the geometry of the object itself becomes the central actor. The complex rotation, potentially driven by a binary core or an extremely irregular shape, creates a force function with sharp, unpredictable edges. The thrust is not constant. It is a series of impulses and torques that depend on the object's orientation to the sunday. This torque-driven dynamics model can account for the more erratic elements of the trajectory that a simple jet model cannot. It transforms the object from a passive body pushed by the solar wind into an active, if unconscious, participant in its own navigation, its path dictated by the asymmetries of its own form. The third, and most profound, level of inference suggests we are witnessing a new class of behavior for interstellar material. This object blurs the ancient taxonomic line between asteroid and comet. It may be a hybrid, an outgassing asteroid, or a comet with a structural integrity unlike anything in our Oort cloud. Its properties challenge our very definitions, suggesting that the population of interstellar objects is far more diverse and exotic than the two data points of Oumuamua and Borisov had led us to believe. This object is not merely an outlier, it is a messenger informing us that our categories are provincial, limited by the singular example of our own planetary system. What other forms, what other modes of existence Might the galaxy be hurling through the void? The immediate consequence of this anomaly is a necessary and fundamental revision of our orbital prediction models. The standard toolkit for calculating the paths of asteroids and comets, honed over centuries, is now revealed to be incomplete for the interstellar context. Any future model must now incorporate an additional highly complex parameter, that of chaotic rotational morphology. The shape, spin state, and internal mass distribution of an object can no longer be treated as secondary concerns. They are primary drivers of its destiny. This complexity, however, opens a new door. For any rapid response mission designed to intercept a future interstellar visitor, the ability to accurately model these non-gravitational forces is paramount. A precise forecast of its path is the difference between a successful rendezvous and a missed opportunity lasting millennia. The erratic dance of 3i Atlas, therefore, is not merely a puzzle to be solved, but a lesson to be applied. It provides the first real-world data to train our next-generation navigation algorithms for deep space. But if its trajectory is governed by such complex and hidden variables, how can we ever hope to predict its future position with the certainty required for a mission? The answer may lie not in the void around it, but in the very substance it is now beginning to shed. For on the 10th of October, the Hubble Space Telescope turned its gaze towards 3i Atlas, and its instruments captured a spectacle that would further deepen the mystery. The data revealed a jet of water vapor erupting from the object with a force and coherence that stunned observers. This was not the gentle, diffuse halo of a typical comet. It was a focused, fire hose-like stream. Preliminary calculations immediately presented a stark contradiction. The radiation pressure from the Sun, the force that would naturally push against such a jet of gas and dust, was demonstrably insufficient to account for the magnitude of the orbital residuals being recorded. The thrust, implied by the water jet, and the thrust needed to explain the object's path, were fundamentally misaligned. This single observation shattered the most straightforward cometary explanation, forcing a reconsideration of the very forces at play. If the visible outgassing cannot explain the motion, then what other, unseen engine is propelling this wanderer? The water, a familiar substance, has become the marker of a profoundly unfamiliar truth. On the 10th of October, 2025, the Hubble Space Telescope turned its mirror towards an object that had already defied simple classification. It was not merely a comet, though it bore the designation 3i Atlas, and it was not an asteroid, though its rocky core was now violently active. The primary data stream revealed a phenomenon of startling intensity, a singular, collimated jet of water vapor and dust erupting from the nucleus with the force and focus of a fire hose. The initial, conventional interpretation pointed immediately to the omnipresent engine of the inner solar system, solar radiation pressure. Photons from the Sun, imparting their minuscule but cumulative push on the comet's dust, could theoretically explain outgassing behavior. Yet, from the moment of this observation, it was clear that radiation pressure was a bystander in this drama, a whisper against a gale. The sheer force and velocity of this water jet, captured in a sequence of high-resolution images, suggested a propulsion mechanism far more potent and directed than the gentle, isotropic nudging of sunlight. Could the simple physics of sunlight truly be responsible for such a violent and focused eruption, or were we witnessing the operation of a far more complex and hidden machinery? The mainstream scientific explanation for cometary activity rests on the premise of subsurface volatiles, primarily water ice, sublimating when warmed. According to current models, as 3i Atlas swung through its perihelion and then past the orbit of Mars, solar heat would have penetrated a thin crust, turning buried ice directly into gas. This gas, seeking escape, would burst through weak points in the nucleus, carrying with it a veil of dust to form the coma and tail. Scientists suggest this could be due to a simple heat transfer, where the water vapor acts as a carrier, dragging particulate matter into the vacuum of space. The laws of thermodynamics and fluid dynamics provide a robust, if generalized, framework for such behavior, one that has been successfully applied to countless other comets from our own Oort cloud. But that model presupposes a certain randomness, a chaotic venting from multiple points across a rotating body. The Hubble data from that day showed something else entirely, a single, persistent, and astonishingly stable jet, its structure remaining coherent over hundreds of thousands of kilometers. If sublimation is a diffuse seepage, what we observed was a precisely engineered nozzle. This leads us to the first speculative hypothesis, that we are not observing simple sublimation, but a geyser-like system with directed vents. Imagine a network of subsurface fractures, not randomly formed, but aligned along structural weaknesses in the object's core. As internal pressure builds from the turning of water ice into gas, these fractures do not burst open chaotically. Instead, they function as a natural nozzle, channeling the erupting vapor into a tight, focused column. The physics is not unlike that of Old Faithful on Earth, but operating in the hard vacuum of space and on a scale of forces that dwarfs any terrestrial analogy. The asymmetric, fan-shaped morphology of the jet, clear in the Hubble imagery, could be the signature of such event, its shape dictated by the intricate topography of the fissure from which it emanates. What geological processes, either from its formation in a distant star system or from eons of cosmic bombardment, could have created such a perfect, natural exhaust port? The data, however, pushes us to consider an even more exotic possibility. The observed increase in the jet's velocity and its peculiar composition, as later corroborated by the Atacama Large Millimeter, Submillimeter Array, ALMA, which detected faint but distinct submillimeter water emission lines, hints at a propulsive efficiency that pure water vapor struggles to explain. This introduces the second hypothesis, that the water vapor is not the sole propellant, but is supercharged by a cargo of nanoscale iron-nickel dust particles. These metallic grains, heated by the sun to extreme temperatures as they are ejected, would transfer their thermal energy back to the surrounding gas, causing a rapid and violent expansion. This process would transform a simple steam vent into a highly efficient, particulate-driven rocket engine. The presence of such metals would point towards a core far richer in differentiated planetary materials than any simple comet. Is it possible that we are observing the natural equivalent of a hybrid rocket fuel, where a volatile fluid is energized by a metallic catalyst, a process commonplace in propulsion laboratories on Earth, but occurring spontaneously in the depths of space? Yet, for such a system to operate with the observed consistency, a sustained and powerful heat source is required. Solar heating is too superficial, too variable with rotation, to account for the deep-seated and continuous energy output implied by the firehose jet. This necessity forces us to the third and most profound hypothesis, an endogenous heat source buried deep within the heart of 3I Atlas. The most plausible candidate, drawn from planetary science, is the decay of long-lived radioactive isotopes, such as aluminum-26 or potassium-40. This is the same primordial furnace that once heated the building blocks of planets in the early solar system, melting ice and driving chemical differentiation. The presence of such a reactor would mean this object is not a simple icy aggregate, but a differentiated planetesimal fragment, a relic from the formation of another planetary system, carrying within it the dying embers of its own creation. Could the relentless, silent ticking of radioactive decay, a process dating back billions of years, be the hidden power behind the dynamic and seemingly youthful activity of this interstellar visitor? The consequences of this jetting activity extend far beyond a spectacular light show. The trajectory of 3I Atlas, meticulously tracked since its discovery, has presented navigational puzzles that cannot be reconciled with the gentle, steady pressure of solar radiation alone, a force astronomers term the beta parameter. The analysis of its path reveals a compelling narrative of interaction. At the first level, we observe that the jet force began to dominate the object's orbital mechanics in the phase following its close passage by Mars. The outgassing was no longer a symmetric force, it had become a primary thruster. The gentle nudge of sunlight was overwhelmed by a series of deliberate, powerful shoves. How does a natural object transition from being a passive body, steered by gravity and light, to an active one, seemingly steering itself? The second level of analysis, derived from the precise timing of brightness variations in the Hubble data, suggests a profound connection between rotation and eruption. The jetting appears to be modulated by the object's spin, pulsing with a periodicity that aligns with its rotational clock. This means the vector of the acceleration force is not constant. It changes direction every few hours. The object is not simply being pushed, it is being steered, its trajectory altered by a force that spins like a celestial garden sprinkler, each pulse imparting a slight change in velocity. This creates a complex, non-gravitational acceleration profile that is a nightmare for conventional orbital dynamicists to model. What master plan, written in the language of rotational mechanics and subsurface plumbing, dictates the timing and direction of these thrust pulses? This brings us to the third and most intricate level of inference, the possibility of a multi-nozzle jet system. The object may not possess one, but several such vents, each a discrete node of activity. These nodes may activate according to their own unique rhythms, perhaps governed by internal heat flow or the opening and closing of subsurface valves. Each active node pilots the orbit with its own specific thrust vector, and the sum of their efforts creates a complex, ever-shifting map of forces acting upon the nucleus. This is not a simple rocket. It is a multi-engined vehicle with an autonomous, albeit natural, guidance system. The resultant trajectory becomes a palimpsest of these individual impulses, a tangled web of accelerations that defies easy decomposition. Can we, with our current mathematical tools, untangle this web to understand the individual voices in this chaotic chorus of thrust? If these hypotheses were to be validated, 3I Atlas would cease to be merely a curiosity and would become a revolutionary natural laboratory. It would demonstrate, in real time, a method of orbital manipulation using targeted gas jets. This is the very principle behind the reaction control systems used on our own spacecraft. To find it operating autonomously on a celestial body provides a priceless template. One day, the lessons learned from observing this interstellar object could be applied to future spacecraft designed to mine water ice from asteroids in the Kuiper Belt or the Main Belt. By drilling into these frozen bodies and using their own water reserves as propellant, we could create self-refueling spacecraft, turning inert rocks into navigable vessels. Has this object, a wanderer from another star, just provided us with the blueprint for the next great era of solar system exploration? A blueprint written not in code, but in the fundamental physics of water and rock? Yet, the forces acting upon this object are not solely internal. As it departed the inner solar system, it carried with it the subtle, cumulative imprint of every gravitational handshake along its journey. The next chapter of this investigation would therefore turn to a seemingly minor player in this grand drama, whose influence may have been quietly recorded in the object's final trajectory. Could the gentle gravity of Mars, a world 10 times less massive than Earth, have left a detectable signature, a faint whisper of a tug that would reveal even more secrets about the true mass and density of this enigmatic traveler? The Martian gravitational field, a subtle and intricate tapestry woven from the planet's internal mass distribution, presents a paradox of scale. Mars, with a mass merely a tenth of Earth's, possesses a gravitational influence that seems, at first glance, negligible on the interplanetary stage. Yet, precision tracking of the interstellar object designated 3I Atlas has revealed a fascinating anomaly. At a specific, critical distance, the gravitational fingerprint of the red planet imprinted itself upon the object's trajectory by a few millionths of an astronomical unit. This is not the grand, sweeping pull that governs planetary orbits, but a whisper of force, a gentle nudge detectable only by our most sensitive instruments. How can a world so small leave such a distinct signature on a visitor from the void? The conventional explanation begins with the most detailed gravitational map of Mars ever assembled. Data from the European Space Agency's Trace Gas Orbiter and the veteran Mars Express, meticulously analyzed through radio science experiments, have refined our understanding of the planet's geoid. These models, expressed through updated spherical harmonic coefficients like J2 and J4, describe the subtle bulges and depressions in Mars's gravity, influenced by the immense mass of Olympus Mons and the profound depths of the Hellas Basin. Orbital dynamicists suggest that 3I Atlas passed through a Grays-level orbit, a trajectory so delicately balanced that it became exquisitely sensitive to these minor gravitational undulations. The slightest perturbation, a faint whisper of gravity, could be amplified into a measurable deviation. Could such a precise and fleeting encounter be purely a product of celestial mechanics, a predictable outcome of a well-mapped field? Yet, the mainstream model encounters its limitations. Doppler tracking data from the object's inbound trajectory, a record of the subtle shifts in its radio signal, registered a series of minute, rhythmic perturbations that do not align perfectly with the predicted gravity field. The residuals, the small differences between the observed path and the calculated one, persist. This opens the door to more speculative hypotheses. The first considers a transient resonance. Perhaps the object did not interact with Mars alone, but with the Martian system, its path momentarily syncing with the rapid orbital dance of the moon Phobos. This fleeting gravitational harmony could have created a micro-resonance, a brief and powerful amplification of the tug experienced by 3I Atlas. Is it possible that the moons of Mars, often considered mere rocky companions, can act as gravitational lenses, focusing and intensifying their planet's pull on specific, unlucky passers-by? A second, more profound hypothesis ventures into the realm of tidal forces. As 3I Atlas approached, the differential gravity across its elongated form would have exerted a torque. Mainstream science would attribute any resultant rotation to simple tidal locking. But what if this interstellar visitor possessed an unusual internal structure, a network of volatile ices trapped beneath a fragile crust? The speculative leap is that the tidal torque did not merely spin the object, but twisted it in a way that fractured this crust, triggering a sudden, jet-like outgassing. The gentle tidal force would have, in effect, switched on a propulsion system, with the gravitational pull of Mars inadvertently pressing the button. Can a gravitational field, by itself, induce active and directional change in a body's behavior, transforming it from a passive projectile into a briefly active one? The third and most radical hypothesis challenges the very symmetry of the Martian world. Our gravity maps, for all their detail, assume a largely homogeneous interior. But what if Mars possesses a fundamentally asymmetric core, a lopsided concentration of dense material left over from its violent formation? Such a mass anomaly would create a slight but sharp gradient in the gravitational field, a hidden knot in the fabric of space-time around Mars. As 3I Atlas sped past, it may have experienced this gradient not as a smooth pull, but as a distinct, almost impulsive tug, a gravitational bump in the road that our current J models fail to capture. This single, amplified jerk could account for the anomalous Doppler shifts. Does Mars hold a secret, unbalanced heart whose occasional beats can be felt only by the most sensitive of interstellar probes? The analysis of this event thus unfolds in escalating layers of interpretation. At the first level, we have the fine-tuning of the existing gravitational field model. The minor residuals in 3I Atlas's path can be partially explained by incorporating even more subtle mass concentrations within the Martian crust, a process of incremental refinement. This is the work of cartographers of force, adding ever finer detail to our maps. But is the simple addition of more data points sufficient to explain a truly unique interstellar event? This leads to the second level of analysis, the concept of a hybrid effect. Here, the gravitational interaction is not seen in isolation. It is coupled with the object's own response. The gravitational tug, perhaps intensified by a lopsided core or a lunar resonance, triggers an outgassing event. The resulting motion is then a complex synthesis of gravitational mechanics and reactive jet propulsion. The trajectory of 3I Atlas becomes a palimpsest, where the forces of gravity and the forces of chemistry are written over one another, inextricably linked. How do we disentangle an innate propulsion from an induced one, when the very act of observation may rely on the interaction that caused it? The third and most profound level elevates the Martian gravitational signature from an anomaly to a tool. The precise measurement of 3I Atlas's deflection has provided humanity with its first controlled experiment in interplanetary microgravity. The flyby was an unintended but perfect test of our ability to detect the most minuscule gravitational influences across the vastness of interplanetary space. This event demonstrates that we can, in principle, weigh a distant object or probe its internal structure by watching how it is bent by the whisper-thin edge of a planet's gravity well. Has a fleeting encounter with an interstellar traveler provided us with a new method for probing the hidden masses of the cosmos? The ultimate consequence of grasping this sensitivity is a new chapter in solar system exploration. By understanding how Mars's weak field can leave a detectable mark, we learn to create exquisitely precise gravitational maps, not just of the red planet, but of all small worlds. This knowledge is paramount for the future of autonomous landing and navigation on asteroids and moons, where weak, irregular gravity fields are the norm, not the exception. A spacecraft must know the local gravity, not in broad strokes, but in fine detail, to navigate safely. Has the path of an object from another star just shown us how to find our own way through the gravitationally complex landscapes of our solar system's smaller bodies? And if we can map the gravity of Mars with such fidelity from a single chance encounter, what secrets might we uncover by intentionally directing our instruments towards the next interstellar visitor, tracing the subtle warps it experiences on its journey through our planetary system? This very act of tracing backwards, of rewinding the celestial clock, promises to reveal a path far more extraordinary than we could have imagined. The celestial mechanics are a clockwork of predictable grace, a ballet governed by the immutable laws of gravity. When we trace the orbits of comets, we expect to see the gentle tug of planetary giants, the subtle push of solar radiation, all woven into a coherent narrative of their journey. The initial trajectory of the object, designated 3I Atlas, however, presented a paradox from the moment its path was calculated. Running the orbital tape backwards, against the flow of time, the object does not emerge from the general direction of the solar apex, the point towards which our Sun moves through the galaxy. A common origin for interstellar visitors swept up in the same galactic current. Instead, its path curves up from the depths of the southern celestial hemisphere, a counterintuitive and deeply unusual point of entry. According to current models of galactic dynamics, an object with such a high relative velocity should, statistically, favor an approach aligned with the Sun's own motion. The initial data suggested an outlier, a solitary rebel cutting against the galactic grain. But does a single anomaly invalidate a statistical expectation, or does it instead point to a more complex and layered truth hidden within the noise? The mainstream scientific explanation posits a simple, if rare, cosmic coincidence. The galaxy is a three-dimensional volume, and the solar system's journey around the galactic center is not a placid cruise on an empty highway. It is a turbulent voyage through a sea of stars, dust, and dark matter, where gravitational perturbations from passing stars can easily deflect a small object onto a radically new course. A close encounter with an unseen star system tens of thousands of years ago could have acted as a gravitational slingshot, hurling 3I Atlas onto its peculiar south-to-north trajectory, making its origin appear anomalous when viewed from our limited temporal and spatial vantage point. This is a perfectly plausible, parsimonious explanation that relies on known physics and the stochastic nature of galactic interactions. Yet, the precision of the trajectory reconstruction, especially the analysis from October 5th to October 12th, 2025, using a new set of residual data, consistently yields a convergent bundle of solutions pointing unambiguously to the southern sky. The statistical confidence in this southern origin is robust. Could a single gravitational kick have been so precise, or does the consistency of the data hint at a more deliberate, systemic origin for this path? This leads us to the first speculative hypothesis, that 3I Atlas originated not from a random stellar backyard, but from a young stellar cluster on the fringes of the galactic disk. These stellar nurseries, rich with the raw materials of planet formation, are dynamic and violent environments. Within such a cloud, the gravitational tides are strong, and the ejection of protoplanetary debris is a frequent occurrence. An object formed in such a region would carry the kinematic signature of its birthplace, a velocity vector distinct from the more sedate field stars of the local galactic neighborhood. Its trajectory, when traced back, would not necessarily conform to the standard model of local stellar drift. The data from the Gaia Data Release 3, when compared to the kinematics of 3I Atlas, show a loose but tantalizing compatibility with the slow, coherent motion of a stellar stream, a ghostly river of stars left over from the cannibalization of a dwarf galaxy or the dissolution of an ancient cluster. Is it possible we are witnessing not a lone wanderer, but a single drop from a celestial river that periodically crosses the solar system's path? To refine this idea further, we must consider the mechanism of its ejection. A solitary star might gently release comets, but a binary star system is a far more efficient catapult. The complex three-body interactions within a binary system can impart tremendous velocity to smaller bodies, easily ejecting them into the interstellar void. Our second hypothesis, therefore, is that 3I Atlas was not merely nudged, but violently kicked from a binary star system through a close gravitational interaction. This would account for its significant hyperbolic excess velocity, a speed greater than the escape velocity of our own Sunday. The energy required for such an expulsion is readily available in the chaotic dance of two stars. The object, then, would be a piece of primordial debris, a fragment of a planetary system that failed to form in a stable environment, now carrying the unique velocity signature of its dramatic birth. Its origin in the southern sky could thus point towards the location of a specific, yet unidentified, binary system capable of such a forceful act of exile. What chaotic scene of gravitational turmoil did this object flee? And what does its composition tell us about the planet-forming processes in such extreme environments? The third and most profound hypothesis builds upon the notion of the stellar stream. It proposes that 3I Atlas is not an anomaly at all, but a representative of a previously underestimated population, a thick traffic of interstellar material flowing along specific galactic currents. Our models of interstellar visitor frequency are based on assumptions of a relatively uniform distribution. But if these objects are predominantly sourced from a few specific, dissolving structures like the stellar stream, its kinematics loosely match, then the interstellar medium in our vicinity is not a homogeneous soup, but is laced with dense, invisible lanes of material. The solar system, in its orbit, periodically plunges through these lanes. The unusual southern entry point of 3I Atlas would then not be random, but the expected entry vector for objects from this particular stream. This transforms our understanding from hunting for rare, isolated wanderers to anticipating scheduled traffic on a galactic highway. How many other interstellar visitors have we missed because we were not looking in the right direction at the right time? The physical evidence from 3I Atlas itself adds a critical and puzzling layer to this kinematic mystery. Early spectroscopic analysis revealed a coma with a dust distribution that was subtly different from typical solar system comets. The color of the dust, a diagnostic tool for composition and particle size, was consistently slightly redder and colder than expected. Comets from our own Oort cloud, forged in the cold and relatively pristine conditions of our system's infancy, have a predictable spectral signature. The dust from 3I Atlas, however, hinted at a different thermal history and perhaps a different mineralogical makeup. The mainstream view would attribute this to the nearly infinite variety of planetary formation environments. Every star system is a unique laboratory, and we should expect the chemical output to vary. The composition of 3I Atlas could simply be a snapshot of one such foreign laboratory, with its slightly colder dust indicating formation farther from its parent star or in a denser, more shielded protoplanetary disk. But does the simple invocation of natural variation suffice when the object itself is already an outlier in its trajectory? The speculative interpretation weaves the kinematics and the composition into a single, more ambitious narrative. What if the colder dust and the anomalous path are two pieces of the same puzzle? The hypothetical stellar stream it may belong to is an ancient structure, a relic of a dwarf galaxy consumed by the Milky Way in the distant past. Stars and their planetary systems that formed in such a satellite galaxy would have done so from material with a different metallicity, a different history of stellar nucleosynthesis. The building blocks themselves would be different. The slightly colder, redder dust of 3I Atlas could be a direct physical sample of this extragalactic origin. It would be a piece of a world that formed not just around another star, but in another galaxy entirely, a tiny fragment of a galactic building block that now, billions of years later, has crossed our path. Are we, then, not just studying an interstellar object, but holding a piece of a cannibalized galaxy in our observational crosshairs? The implications of this are profound, reshaping the future of interstellar object science. If this southern stream is a real feature, a consistent source of such visitors, then our observational strategy must evolve. Instead of passively waiting for the next anomaly to appear, we can actively prepare. Future telescopes, like the Vera C. Rubin Observatory, could be programmed to conduct targeted surveys of these specific celestial coordinates, these predicted entry corridors. We could shift from a paradigm of chance discovery to one of strategic interception. This would open the golden age of opportunity, a planned campaign to encounter and study interstellar material. We could deploy dedicated spacecraft, waiting in orbit, ready to be dispatched on fast intercept trajectories to the next confirmed visitor from this stream. The discovery of 3I Atlas's path is not merely an answer to a question of origin, it is the key to a new methodology. But can we develop the foresight and the resources to position ourselves along this celestial river, ready to cast our nets into the cosmic current? As we contemplate the grand implications of its origin, our attention is drawn inexorably to the moment the object began to reveal its true nature, a transformation as dramatic as it was unexpected. For the path an object travels is only the prelude to the story of its being, a story that began to violently unfold as it approached the furnace of our Sunday. What hidden forces, locked within its icy heart, were awakened by the solar flame, and what did the resulting cataclysm reveal about the internal architecture of this wanderer from the void? The void of interplanetary space is not truly empty, but it is a place of profound stillness, where the only constant is the relentless, gentle push of sunlight. On the 30th of October, 2025, as Comet 3I Atlas fell ever closer to the Sun, this stillness was shattered, The comet, a nomad from another star, transformed itself. It became a machine, a celestial fountain of its own, violently expelling its essence into the vacuum. In a matter of hours, a significant fraction of its mass was lost, and with it, the very spin of its nucleus began to change. This was not a gentle evolution, but a violent, rapid metamorphosis, a desperate struggle between gravity and volatility, played out on a stage of ice and dust. What internal cataclysm could force a worldlet to reconfigure its very rotation so abruptly? Mainstream planetary science offers a framework for such outbursts. According to current models, as a comet approaches the Sun, subsurface ices, primarily water ice, but also pockets of more volatile substances like carbon monoxide, begin to sublimate. The pressure builds beneath a crust of non-volatile material until it finds a weakness, rupturing in a jet of gas and dust. The reaction force from such a jet acts like a tiny natural thruster, imparting a torque on the nucleus. If a jet persists from a single region, it can, over time, alter the comet's rotation period and even the orientation of its spin axis. This is the established physics of non-gravitational forces, a phenomenon meticulously documented in countless comets from our own solar system. The observed precession, the wobble in the rotation, increasing in tempo, as recorded by the Hubble Space Telescope and NEOWISE, fits neatly into this paradigm of asymmetric outgassing. Could such a well-understood process, scaled up in intensity, be the sole architect of this dramatic event? However, the scale and violence of the event on the 30th of October defies a simple scaling of known principles. The conventional jet model accounts for a steady push, but it struggles to explain the machine gun-like rapidity of the outbursts, the sheer magnitude of mass loss inferred from the photometric data, and the breathtaking speed with which the light curve's 6-hour period shifted phase. The Hubble and NEOWISE data show not a smooth curve but a jagged, frantic series of peaks and troughs, a stellar seismograph recording a series of internal convulsions. The conventional model of a sealed pressure cooker does not account for the orchestrated, sequential detonations that seem to ripple across the nucleus. What if the trigger mechanism was not merely solar heat, but a chain reaction of structural failures deep within the comet's heart? This leads us to a more speculative, yet compelling, first-level hypothesis. Imagine not a simple layer of crust over ice, but a complex, stratified core. Comet, 3I Atlas, forged in an alien protoplanetary disk, may possess a layered architecture of ices with different volatilities, a brittle, porous matrix of water, ice riddled with super-volatile pockets of carbon monoxide and carbon dioxide. As the sun's heat penetrated, it did not create a uniform layer of gas, but a network of pressurized cavities. The initial outburst may have acted not as a simple release valve, but as the detonator of a larger charge. The sudden loss of overlying material and the resultant shift in internal stresses could have triggered a cascading collapse of these volatile pockets, a series of internal steam explosions propagating through pre-existing weaknesses. This would be less like a geyser and more like a demolition, where the removal of one key support brings down the entire structure in a controlled, yet violent, sequence. Was the comet experiencing not just outgassing, but a form of internal, cryovolcanic quake? The evidence for such a cataclysm is etched into the light. The rapid change in the light curve's phase is the key. A simple jet would impart a gradual torque, slowly changing the rotation. The observed data, however, suggests a near-instantaneous reconfiguration. The precession, the wobble, accelerated dramatically. This implies a significant and rapid redistribution of mass, or more precisely, a significant and rapid loss of mass from a specific region, effectively shifting the object's center of mass and its principal axis of rotation in a single, traumatic event. The kinematic models derived from the photometry do not show a gentle push, but a violent shove. How much of the comet's interior architecture had to be violently excavated to cause such a fundamental shift in its celestial mechanics? This cascading failure leads us to a second, more profound hypothesis. The steam explosion through a bottleneck model, while evocative, may be too localized. What if the heat from the sun did not just create subsurface pockets, but initiated a runaway feedback loop within the comet's very fabric? We can postulate the existence of a superheated zone, a region on the nucleus where the geometry and composition allowed for an unprecedented accumulation of thermal energy. Within this zone, the sublimation of ices would not be a steady process, but a cyclical, violent one. As a vent opens and a jet erupts, it clears the area, exposing fresh, pristine ice to the full fury of solar radiation. This triggers an even more violent sublimation event, which seals the vent with ejected debris, only for pressure to build once more. This creates a self-perpetuating, pulsing jet, a chain of fountains firing in rapid succession. This would be a cold firestorm, a cyclical cataclysm of the comet actively consuming its own substance in a frantic, rhythmic expulsion. Could such a natural, oscillating engine be powerful enough to not only expel mass, but to torque the entire nucleus within a single orbital pass? The smoking gun for the primary driver of this event lies in the chemistry of the expelled material. Narrowband imaging focusing on the hydroxyl radical, a direct byproduct of the photodissociation of water vapor, revealed a sudden, orders of magnitude increase in water production. This was not a gradual rise, but a spike, a veritable flood of water molecules being liberated into the coma. This data strongly suggests that the primary volatile involved was indeed water ice, the most fundamental of cometary materials. The sheer volume, however, points to a reservoir being tapped that was not merely surface level, but deeply buried, a cache of ice suddenly exposed and vaporized all at once. What vast subterranean chamber of ice was breached to release such a deluge? The analysis of this event thus unfolds in escalating tiers of implication. The first level is the direct consequence. Mass loss leads to a shift in the spin axis. This is basic Newtonian physics. Change the distribution of mass in mean, a rotating body, and you change its rotation. The second level is more complex. The induced precession, now stronger and more chaotic, itself begins to reconfigure the very outgassing that caused it. As the nucleus wobbles, new regions are thrust into direct sunlight, while others fall into shadow. This can activate dormant jets and silence active ones, creating a feedback loop where the rotation drives the outgassing pattern, which in turn drives further changes in the rotation. The comet becomes a self-modifying engine, its activity and its spin locked in a frenetic dance. How long can such a positive feedback loop continue before the system tears itself apart? This naturally compels us to consider the third and most extreme level of analysis, rotational instability, as a pathway to fission. The torques imparted by such violent, asymmetric outbursts do not merely change the spin, they can induce stresses that approach the gravitational binding energy of the nucleus itself. If the rate of spin exceeds a critical threshold, the centrifugal force can overcome the meager gravity holding the rubble pile structure together. The precession itself, a wild, gyrating motion, introduces complex shear stresses throughout the interior. The result could be the development of macroscopic fractures, a cracking of the nucleus along fundamental fault lines. The cometary quake hypothesis then reaches its logical and terrifying conclusion, not just a rearrangement of surface features, but a fundamental structural failure of the body itself. Did the events of the 30th of October bring Comet 3I Atlas to the very brink of disintegration? The practical ramifications of witnessing such a natural phenomenon extend far beyond mere academic curiosity. This event was a masterclass in celestial mechanics, a demonstration of a spin engineering technique performed on a planetary scale. It teaches us that a body's attitude can be controlled not by complex chemical thrusters and heavy fuel loads, but by the careful, directed management of its own inherent resources. The comet used its water vapor, a resource readily available on many small bodies, as its propellant. A future spacecraft, stranded or needing a course correction, could theoretically emulate this process. By focusing sunlight onto a specific patch of surface ice to create a controlled jet, a vessel could alter its rotation or even its trajectory using recycled water and solar energy as its only fuel. This is in situ resource utilization pushed to its logical extreme, turning the very body of an asteroid or comet into its own propulsion system. Have we just observed the blueprint for a new paradigm in deep space navigation, written in the erupting geysers of an interstellar visitor? As the vast plume of vaporized water and dust from the great outburst began to dissipate, spreading into the growing coma, it set the stage for an even more perplexing and counterintuitive sight, one that would challenge our very perception of how these celestial objects present themselves. For when the Catalina Sky Survey trained its telescopes on the comet in the weeks that followed, it captured an image that should not, according to simple textbook diagrams, have been possible. In the quiet vacuum between the orbits of Mars and Jupiter, a routine patrol of the Catalina Sky Survey was underway in mid-October 2025. Its automated telescopes, ceaselessly scanning for near-Earth objects, captured a sequence of images that would momentarily halt the scroll of celestial routine. There, in the precise data streams, was the object designated 3I Atlas, a confirmed interstellar visitor, but it presented an anomaly that defied immediate comprehension. Projecting from its nucleus, opposite the sweeping curved dust tail that trailed behind it in its journey, was a needle-straight spike of light, pointing directly towards the sunday. This was an anti-tail, a phenomenon of rare and deceptive geometry, appearing here with an unnerving clarity and persistence. According to current models of cometary science, an anti-tail is not a separate structure, but an artifact of perspective. It is thought to be composed of larger, millimeter to centimeter-sized dust grains, too heavy to be easily pushed by the gentle pressure of solar radiation. These grains tend to be shed by the comet and remain largely within the plane of its orbit, forming a thin, disc-like sheet of debris. When the Earth's orbit carries our line of sight through the edge of this sheet, we see it projected as a narrow, bright line pointing sunward. The initial analysis of the Catalina data from the 12th to the 18th of October seemed to support this. Photometric measurements indicated a population of particles significantly larger than the fine dust that constitutes the main tail, particles that would indeed resist the solar wind and cling to their orbital path. This was the classical explanation, a trick of light and orbital mechanics playing out on a cosmic stage. But could a simple trick of perspective account for the anti-tail's razor-sharp definition and its stability over several days, a feature rarely so pronounced in any comet of local origin? The conventional explanation rests upon a passive cloud of dust, a mere residue left in the comet's wake. Yet, what if the process were more dynamic? A speculative hypothesis suggests that 3I Atlas was not merely shedding dust, but actively ejecting it in a highly collimated jet. This would not be a random, isotropic emission, but a focused stream of particles launched along a specific plane, potentially the equatorial plane of the rotating nucleus. If this jet were precisely aligned with the orbital plane, and if our viewpoint from Earth coincided perfectly with its edge, the effect would be a brilliantly defined, linear anti-tail. The larger particle sizes detected would be a natural consequence of such a mechanism, as finer dust would be more readily dispersed by radiation pressure, while heavier grains would maintain their coherent trajectory. Observational support from the Atlas HKO site in Hawaii and the global Las Cumbres Observatory Network confirmed the phenomenon was real and stable, a feature not unambiguously identified in the previous interstellar visitors, 1I Oumuamua or 2 I. Borisov. This alignment of a potential jet with our line of sight seems almost too perfect to be mere coincidence, does it not? This leads to a more profound, a more electrically charged possibility. The laws of physics governing the interaction of a comet with the solar wind are well established. The ion tail, composed of charged molecules, is always directed away from the Sun by the relentless flow of the heliosphere. But what of neutral dust? The third hypothesis ventures into the realm of plasma cosmology, proposing that the intense electric field of the solar wind near the Sun could induce charges on these larger dust particles. Once charged, they would no longer be neutral bystanders. They would become susceptible to electromagnetic forces, potentially aligning themselves along the local magnetic field lines embedded within the solar wind. This would not be a simple sheet of debris, but a structured conduit, a tube of guided dust, painting a line directly back to the heart of our solar system. The antitail, then, would transform from a passive shadow into an active indicator of a complex, unseen plasma-comet interaction. Is it possible we are witnessing not just reflected sunlight, but the visible tracer of a fundamental force sculpting the very fabric of this visitor's composition? The implications of this antitail extend far beyond its initial, puzzling appearance. For 3I Atlas, this structure became a unique measuring stick for its population of large dust grains. These are not the ephemeral particles that fill the comae of short-period comets. These are substantial fragments, perhaps pebbles, and small stones that hold within them a history untold. They are a direct sample, delivered across the light years, of the building blocks of a planetary system born around another star. Their size and distribution, quantified by the photometry of the antitail, provide a priceless dataset. They suggest that in whatever cold, distant cradle 3I Atlas was formed, the conditions were favorable for the growth of material beyond mere dust, hinting at processes of accretion that may be universal. But could these same particles, whose behavior might be governed by electromagnetic forces, also point the way to a new technology for traversing the void? The existence of a potential plasma-guided dust trail invites a radical thought. If we can learn to manipulate charged particles in the tenuous solar wind, could we one day engineer similar structures? The concept of a plasma sail, using magnetic fields to catch the solar wind, much like a ship's sail catches the wind, is known to advance propulsion research. The antitail of 3I Atlas acts as a natural laboratory, demonstrating how a celestial body can create and maintain a coherent stream of matter across millions of kilometers, using nothing but the innate forces of our star. By studying this natural phenomenon, we may uncover the principles for creating artificial versions, dust sails, that could propel future spacecraft on journeys to the outer planets and beyond. The visitor has not only brought a message from the galactic void, but perhaps also a blueprint. What other secrets of interstellar travel are written in the dust of this passing stranger? Yet, the light we see is only part of the story, for it is the specific quality of that light, its hidden polarization, and the elemental secrets locked within its spectrum that would soon challenge our understanding of this object's very origin. As telescopes larger than those used for survey work turned their gaze towards 3I Atlas, they sought to dissect its glow with finer and finer precision, searching for a signature in the light that would be impossible to fake. The light we gather from the depths is more than a mere beacon. It is a complex message, a whisper of elemental truths encoded in its very essence. As the reflected sunlight from the interstellar object 3I Atlas was captured and dissected by the world's most powerful observatories, it presented a conundrum wrapped in a metallic gleam. The initial spectroscopic analysis, a routine procedure for any celestial visitor, returned a ratio of nickel to iron that stands in stark defiance of all known cometary bodies within our own solar system. Every comet we have ever studied, from the primordial ice of the Oort cloud to the rocky interlopers from the asteroid belt, adheres to a certain chemical proportion, a signature of our solar system's specific conditions of birth. 3. I-Atlas does not. Its light tells a story of a place where nickel is not a trace element, but a fundamental constituent. Could our local neighborhood be but a single, chemically mundane province in a galaxy of far greater diversity? The mainstream explanation posits a straightforward, if unusual, origin. According to current models of planetary formation, the inner regions of a protoplanetary disk, closer to the heat of the young star, are where heavier metals like iron and nickel tend to condense. It is conceivable that 3I originated from such a metal-rich zone, a fragment of a differentiated body where nickel was abundant. This could be the result of a cataclysmic collision in a distant system, a violent event that ejected a core fragment or a chunk of a metallic mantle into the interstellar void. The observed nickel-over-iron signature would thus be a natural geological fingerprint, a direct snapshot of an alien planet's interior now exposed to the vacuum of space for the first time. But does this model adequately explain the sheer purity of the signal, the lack of significant dilution from the silicate crust that should, by all rights, encapsulate such a metallic core? This leads us to a more speculative hypothesis. Perhaps we are not looking at a naturally vaporized nickel-rich region, but at something far more structured. The first fictional layer suggests a deliberate exposure, a cold metallic reflection intentionally presented to the universe. The second, more profound idea proposes that this object is not a mere fragment, but a salvaged piece of a metallic planetary core, a planetesimal torn from its stellar cradle in an ancient galactic upheaval. And the third, most challenging concept is that the anomalous polarization and spectral data are not a product of natural geology at all, but a form of optical noise, a sophisticated reflective coating designed to cloak an artificial structure of unimaginable purpose. What if the metal is not just a component but the message itself? The empirical evidence supporting this metallic anomaly is both precise and compelling. In mid-October 2025, a coordinated observational campaign utilizing the Subaru telescope and the Very Large Telescope trained their instruments on the object. Polarimetry, the study of the orientation of light waves, revealed a curve that deviated significantly from the standard model for light scattering off cometary silicate dust. The light from 3I was polarized in a way that suggested a smoother, more reflective surface than any known natural body of its size. Simultaneously, infrared spectroscopy uncovered a powerful, unexpected absorption band, indicative of nickel oxide, while the signature for iron oxide was conspicuously weak. A direct comparison with the pristine samples of comet Wild 2, returned to Earth by the Stardust mission, highlighted the stark contrast. The nickel-to-iron ratio in 3I was more than double that of any sample in our possession. Is this the first tangible evidence of a fundamentally different pathway of cosmic chemistry, or are we comparing a simple rock to a forged alloy? The analysis of this data invites a cascade of inferences, each level venturing further into the unknown. At the first level, we must simply accept the presence of a rich nickel source within the object's parent cloud, a region of space where the elemental building blocks were simply different from our own. This alone would force a revision of our galactic chemical models. At the second level, we must consider that the home star system of 3I possessed uniquely extreme conditions for natural metallurgy, perhaps a system with an unusually high neutron flux from a nearby supernova, or one where gravitational interactions created pressure and temperature regimes that favored the segregation and concentration of nickel over iron. But what natural process could achieve such a clean separation, leaving such a distinct and unadulterated signature across the entire surface of the object? This brings us to the third and most speculative level of analysis, the possibility of refinement. The purity and the specific reflective properties hinted at by the polarimetry data could be interpreted as signs of processing. The material may not have been merely formed, but intentionally refined and shaped. It carries the potential hallmark of technology, not geology, a signature of deliberate action rather than chaotic cosmic forces. This would not be a natural ore, but a product. If this is the case, then the anomalous nickel-iron ratio is not a quirk of nature, but a designed feature, a beacon of elemental composition meant to be read by anyone who knows how to look. Could 3I Atlas be a metallic message in a bottle, a relic of a civilization that learned to write its history not on stone, but in the very atomic structure of its artifacts? The implications of these possibilities are profound and divergent, each path leading to a different future for our understanding of the cosmos. If the artificial hypothesis holds even a grain of truth, then 3I Atlas is no mere wanderer, it is a courier. It becomes a metallic letterbox, a silent archive carrying the condensed knowledge, or perhaps the mere announcement, of a civilization lost to time. Its passage through our solar system would be the single most important event in human history, a delivery from the depths of time and space. Conversely, if a natural explanation prevails, its impact is scarcely less revolutionary. It would dramatically expand our understanding of chemical diversity across star systems, proving that the processes we observe locally are not universal laws but local bylaws. It would be the first step towards a true interstellar geochemical map, revealing the vast and varied mineralogy of the galaxy. But does the object's strange behavior end with its chemical makeup, or does its physical motion hold further clues to its enigmatic nature? For as we attempted to map its surface through photometric observations, another layer of mystery unveiled itself. The Hubble Space Telescope, in a series of high-cadence images spanning 6 hours, recorded a light curve that was anything but stable. The predictable brightening and dimming that one would expect from a steadily rotating body was absent, replaced by a fluctuating cycle that suggested a rapid and chaotic change in its rotational state. The period of its spin appeared to be in flux, a characteristic that is exceptionally rare for a body of its supposed size and age. What force could possibly be acting upon it to cause such a dramatic and rapid alteration in its fundamental dynamics? The conventional astrophysical toolbox offers one immediate explanation: outgassing. As a comet approaches the Sun, solar heating sublimates its volatile ices, creating jets of gas that erupt from its surface. These jets can act like thrusters, imparting torque and causing the object to spin up, spin down, or begin to precess. This is a well-documented phenomenon for solar system comets. Scientists suggest that 3I Atlas, despite its unusual composition, must still harbor some volatile components deep within its structure. The asymmetric venting of these gases, as the Sun's heat penetrates its crust, could be the engine driving its rotational instability. This is a perfectly rational, physically sound model that requires no new physics. Yet, it rests on the assumption that the object's internal structure is heterogeneous, with pockets of volatiles that can be unevenly heated, an assumption that the remarkably uniform and metallic spectral signature seems to challenge. However, certain anomalies still defy this straightforward explanation. The speed of the rotational change, as calculated from the Hubble data, is remarkably aggressive. For outgassing to produce such a rapid precession, the jets would need to be both incredibly powerful and located at points of maximum leverage on the object's structure. Furthermore, the light curve does not show the smooth, predictable changes indicative of a single, stable jet, but rather a series of erratic fluctuations. This introduces a more speculative hypothesis. What if the cause of the instability is not natural outgassing, but something else entirely? What if the torques acting upon it are not from random vents, but from a source of controlled propulsion, or perhaps from the movement of internal components? The object's changing spin state could be the result of a malfunctioning stabilization system, or even the faint, detectable signature of operational machinery within, struggling to maintain a course after eons of silence. Is the object tumbling because it is dead, or because it is, in some way still alive. The analysis of this dynamic behavior also proceeds through escalating tiers of interpretation. At the first level, we are observing a simple, if extreme, case of cometary outgassing from a uniquely rigid body, a testament to the violent effects of solar heating. At the second level, the instability hints at a profoundly asymmetric internal structure for 3I Atlas, perhaps a density distribution so irregular that it points to an artificial origin, a collection of disparate modules loosely held together, whose shifting mass contributes to the wobble. And at the third, most profound level, the rapidly changing rotation is not a symptom of chaos, but a form of modulation. The varying light curve could be a means of communication, a slow, deliberate blinking by an object that uses its entire body as an antenna, its spin state carefully, or perhaps desperately, controlled to broadcast its condition. Are we witnessing the death throes of a machine, or is its erratic dance a carefully choreographed signal? The outcome of this line of inquiry forces us to confront the very nature of motion in space. If the precession is natural, it provides a fascinating case study in the orbital mechanics of interstellar objects, revealing how such bodies evolve under the influence of stellar radiation. It would become a textbook example of non-gravitational forces at work. But if even a fraction of the speculative hypotheses hold weight, then the changing spin is not a passive effect, but an active characteristic. It would mean that 3I Atlas is not simply moving through space, but is interacting with it in a complex manner. Its path is not just a Keplerian arc, but a trajectory influenced by its own internal state. This leads us to the ultimate question, one that requires us to look not at the object itself, but at the empty space it has traversed for eons. For if it is artificial, or even just actively maneuvering, its journey would not be a random walk, but a guided one, and its point of origin would hold the key to everything. Where, in the immense and starry blackness, did this enigmatic traveller truly begin, and what awaits at the end of the long, silent road it has been following? The light curve of the interstellar visitor, designated 3I Atlas, presented a profound anomaly in the closing days of its solar encounter. Over a mere 6-hour window, its brightness did not pulse with the predictable regularity of a simple rotating body. Instead, it oscillated with the frantic, arrhythmic cadence of a fibrillating heart, a signature utterly unlike anything observed in a natural celestial body. This was not a spin, it was a stagger, a violent, unbalanced dance against the backdrop of the void. The data streaming from the Hubble Space Telescope in October 2025 painted a clear and unsettling picture. The amplitude of these luminous oscillations had doubled, a direct testament to an object in the throes of a profound rotational instability. The conventional explanation points to outgassing. As solar heating sublimates volatile ices from the object's surface, the resulting jets act like miniature thrusters. According to current models, an asymmetric distribution of these active vents could easily generate a net torque, altering the object's spin state. The changing spin vector, reported by the European Space Agency's tracking data, would be a natural consequence of this process, a predictable, if complex, physics of a dirty snowball warming in the sunday. But does a simple dirty snowball, a remnant of a distant planetary system, possess the structural integrity to withstand such violent, self-inflicted forces without flying apart? The photometric phase models, derived from that frantic 6-hour light curve, suggest a more dramatic reality. They indicate that the object's rotation period was shortening at an alarming rate, decreasing by 15%. A jet-induced torque could explain a gradual change, but such a rapid spin-up implies forces acting with startling efficiency. This leads to the first speculative hypothesis, that we are not witnessing simple surface-level outgassing, but a sustained, internal gas plume thrust, a continuous expulsion from a pressurized reservoir that acts as a constant, unbalanced engine. Imagine a celestial Catherine wheel, not just sparking, but being whipped into a frenzy by its own internal fury. The radar profile from the Goldstone Observatory, showing a distorted reflection pattern that changed from day to day, supports the idea of an object whose very shape is being morphed by these forces. Could the internal structure of 3I Atlas be engineered to utilize such forces, a form of natural propulsion that we have yet to comprehend? To account for the chaotic high-amplitude wobble, the arrhythmic pulse, one must consider a more profound disturbance than mere jetting. The mainstream view might suggest a recent, slight impact or a massive, sudden outburst that triggered a precession. This is a known phenomenon, where a torque applied to a rotating body causes its axis of rotation to slowly trace out a cone. Yet, the wild amplitude of the wobble, the sheer violence of the photometric signature, challenges this. It suggests a body with an extraordinary mass distribution. This brings us to the second, more daring hypothesis, that 3I Atlas possesses a binary nucleus. Two distinct cores, perhaps in a loose contact orbit, where even a minor interaction or tidal force could set the entire conglomerate into a violent, chaotic precession. The gravitational dance of two cores would not produce a clean spin. It would generate a tumultuous roll, a drunkard's walk through space, perfectly mirroring the erratic light curve. But what if this duality is not a natural formation, but a functional one? The most radical interpretation of the data pushes beyond a binary nucleus to the object's fundamental composition. The rapid evolution of the spin state, and its apparent long-term instability, persisting for days without the object disintegrating, points towards a structure of exceptionally low density and high strength. The third and most speculative hypothesis envisions a hollow core, not a cavern of ice and rock, but an intricate, rigid framework, a geodesic dome on a cosmic scale, perhaps constructed from exotic, crystalline ices or carbonaceous filaments. This would explain the radar anomalies and the object's ability to withstand tremendous rotational stresses. A hollow body would have a moment of inertia, entirely different from a solid one, leading to wild, unpredictable gyrations under the slightest force, much like a rattleback toy that spins stably in one direction but wobbles violently in the other. Its rotation would not be a simple state, but a fragile, dynamically unstable condition, perpetually on the verge of cascading into chaos. Is the ultimate truth of this tumbling object not its material, but its geometry, a geometry that defies natural formation? This analysis, therefore, unfolds in escalating tiers of implication. At the first level, the changing spin axis is a direct, mechanical consequence of asymmetric outgassing, a straightforward transfer of momentum from expelled gas to the rigid body. Yet, this simple explanation fails to capture the full chaos. The second level of analysis acknowledges that these are not steady jets, but likely violent, episodic, and uneven eruptions. This unsteady thrusting does not impart a smooth torque, but rather hammers the object, inducing a chaotic wobble superposed on its main spin. A turbulent state that constantly feeds energy into its rotation. But what source of volatiles could sustain such violent, persistent outgassing so far from the Sun? The third and deepest level of inference concerns the long-term instability. A solid body would eventually stabilize or fracture. The continued survival of 3I Atlas in this hyperactive state suggests an internal structure that is not only hollow, but engineered to be metastable. The very forces that cause its wild dance are the same forces that prevent its immediate disintegration, a delicate balance that could, theoretically, lead to a controlled self-fracture. Was this tumultuous rotation not a sign of breakdown, but a pre-programmed maneuver? The implications of deciphering this self-correcting spin mechanism are profound for human technology. Our satellites and space probes rely on reaction wheels and chemical thrusters for attitude control, systems with limited lifespans and complex fuel requirements. If the principle behind Three-Eye Atlas's chaotic dance could be understood and harnessed, it would revolutionize aerospace engineering. One could envision future probes with no moving mechanical parts, their orientation controlled entirely by the precise venting of internal gas plumes. Using the very principle that sent this interstellar object into its mad waltz, such a system would be simpler, more reliable, and potentially capable of maneuvers beyond the scope of conventional technology. But to unlock this secret, we must first determine if we are observing a natural accident of physics or the functional architecture of a navigable object. And as this solitary traveller continued its tumbling path through our solar system, it was about to pass before a coordinated array of eyes, unlike any ever deployed. A fleet of observers waiting at the planet Mars. The week spanning the 1st to the 7th of October, 2025, presented a celestial alignment of profound scientific consequence. For 7 days, the planet Mars, that rust-coloured sentinel of the inner solar system, transformed from a solitary world into a coordinated astronomical platform. An armada of robotic explorers, the Trace Gas Orbiter, Mars Express, and MAVEN, all assets of the European Space Agency and NASA, ceased their primary missions of planetary scrutiny and turned their instruments outward. Their collective gaze was fixed upon a single enigmatic target, the interstellar object designated Three-Eye Atlas, as it performed its silent, high-velocity transit through our cosmic neighborhood. This unprecedented maneuver, the Mars Armada, was not merely a matter of convenience but a deliberate orchestration to create a multi-perspective observational baseline, a feat never before attempted for an object from beyond our star system. What unique properties of this visitor demanded such a concerted effort, and what could be learned from viewing it through multiple sets of electronic eyes simultaneously? According to current models of orbital dynamics and observational astronomy, the primary advantage of this distributed network was geometric. A single observatory, whether on Earth or in space, can only provide a two-dimensional projection of an object's path. By utilizing 3 separate spacecraft in distinct orbits around Mars, scientists could triangulate the position of Three-Eye Atlas with exquisite precision. This method, akin to celestial cartography, would allow for the most accurate determination of the object's trajectory and velocity yet achieved, potentially refining our understanding of its origin point within the galactic disk. Instruments like the Nomad spectrometer suite on the Trace Gas Orbiter and the SpyCam instrument on Mars Express were tasked with capturing the object's spectral signature across different wavelengths, building a composite chemical profile that would be resilient to the biases of any single instrument. The scientific rationale was clear and methodical: to gather a robust, multi-point dataset that would minimize observational error and provide a definitive account of the object's physical characteristics. Yet, one must ponder, if the goal was merely enhanced precision, would the immense logistical effort of coordinating an entire fleet of interplanetary probes be truly justified? This leads us to a more speculative yet compelling hypothesis. The coordinated operation of the Mars Armada may have been an attempt, whether by design or by emergent opportunity, to create something far more sophisticated than a simple triangulation network. By synchronizing the data streams from the Trace Gas Orbiter, Mars Express, and MAVEN, and processing them through sophisticated correlation algorithms, the ensemble could theoretically function as a single, colossal instrument, a planetary-scale interferometer. On Earth, radio astronomy interferometers like the Very Large Array combine signals from multiple dishes to simulate a telescope aperture dozens of kilometers wide, granting them unparalleled resolution. The Mars fleet, separated by thousands of kilometers, could, in principle, achieve a similar feat, resolving fine details on the surface or in the coma of Three-Eye Atlas that would be utterly invisible to any single telescope. Creating patterns of constructive and destructive wave interference, that reveal structures at a scale previously unimaginable for an object so distant. Could the faint whispers of radio emission or the subtle variations in reflected sunlight have contained a level of detail that only a virtual eye of this magnitude could perceive? The very presence of Mars itself introduces another layer of profound possibility. The Martian atmosphere, thin though it is, and its lack of a global magnetic field create a unique environment for observation. Free from the radio noise and light pollution that plague Earth-based observatories, and absent the distorting effects of a dense ionosphere, the planet offers a relatively pristine window to the cosmos. In this context, the armada of orbiters did not just use Mars as a vantage point, they effectively turned the entire planet into a natural component of their observational system. Mars became, for 1 week, a stable, rocky platform upon which humanity's first interstellar observatory was temporarily constructed. Its gravity well anchored the delicate geometry of the interferometer, while its bulk shielded the instruments from the solar wind at precise orbital phases, potentially allowing for the detection of signals too faint to be discerned otherwise. Was it merely a convenient orbital mechanic, or did the unique astrophysical qualities of Mars itself play an active role in amplifying our ability to listen? The data returned during this week was as unprecedented as the campaign itself. The European Space Agency reported that for the first time in history, a simultaneous, multi-source, interplanetary spectrum of an extrasolar object had been captured. The spectrometers NOMAD, SPICAM, and the Neutral Gas and Ion Mass Spectrometer, or NGMS, on MAVEN, all contributed their unique data slices, painting a composite picture of 3I Atlas's composition in light, infrared, and ultraviolet. The initial analysis, the first level of interpretation, confirmed the mission's foundational goal. The combined data allowed for a hyper-accurate orbital fix, refining the object's path through the solar system to a degree of certainty that would become the new standard for all future studies. But was the true value of this dataset contained solely in the refined trajectory of this interstellar wanderer? The second level of analysis delves into the more subtle implications of the interferometric data. The minute differences in the signal received by each spacecraft, the slight Doppler shifts and timing delays, hold a wealth of information beyond simple location. These anomalies, when processed, can reveal the internal structure of the object's coma, the cloud of gas and dust surrounding it. They could map density fluctuations, pinpoint regions of outgassing, and potentially even discern the rotation state and gross topography of the nucleus itself. The interference patterns become a diagnostic tool, allowing scientists to peer into the turbulent dynamics of this ancient traveler. The conventional explanation suggests this would reveal a simple, comet-like structure of ices and dust. Yet, what if the patterns of gas and dust ejection were not random, but exhibited a complexity or symmetry that defied the simple sublimation models of a generic icy body? This brings us to the third and most profound level of inference from the Mars Armada event. The successful operation of this distributed network did more than just study an interstellar object. It fundamentally demonstrated a new paradigm for human exploration. For those 7 days in October, Mars truly became humanity's first operational extrasolar observatory. It proved that our robotic emissaries, scattered across the solar system, can be repurposed and woven into a cohesive, scientific instrument of staggering scale and capability. This was not a mission to a planet, but a mission using a planet as a tool for looking beyond. The Mars Armada is the direct precursor to a future deep space array, a network of observatories spanning the orbits of Mars, Jupiter, and perhaps even farther, creating a virtual telescope with a baseline of hundreds of millions of kilometers, capable of directly imaging the surfaces of exoplanets. The event proved the concept. But does the very success of this experiment suggest that our future in understanding the cosmos lies not in building ever larger single telescopes, but in orchestrating the silent fleet we have already scattered amongst the worlds. The faint, complex signals recorded by the Armada, the subtle interplay of light and shadow across the faces of 3 separate spacecraft, have written a new chapter in astronomy. They have shown that our reach can extend far beyond our immediate location through coordination and intellect. The data streams, now fused into a single, monumental dataset, continue to be parsed, offering revelations that will likely unfold for years to come. Yet, one particular dataset, concerning not the object's trajectory or structure, but its volatile content, would soon demand the attention of another legendary observatory, one closer to home. For if the Mars Armada mapped the grand architecture of the visitor's passage, what secrets would be revealed by measuring the very substance of its bray? Life, the water bleeding into the void? As the Mars Armada completed its historic vigil, the torch of observation was passed to an older sentinel of the skies, the Hubble Space Telescope. From its vantage point in Earth orbit, Hubble began an equally critical task: to monitor not the object's path, but its vital fluids. From the 8th to the 14th of October, 2025, Hubble's sensitive instruments were trained on 3I, Atlas, meticulously tracking the loss of water vapor from its surface. The data it returned was startlingly precise, establishing that the rate of outgassing reached a peak velocity of 1.2 kilograms per second. This was not a steady trickle, but a forceful, episodic jet, a geyser erupting in the hard vacuum of space. This quantitative measurement of mass loss provided the first hard data with which to calibrate the non-gravitational forces acting upon the object, the subtle pushes and nudges from its own outgassing that slightly alter its path from a pure gravitational trajectory. But what underlying mechanism could generate such a precise and powerful outflow from a body supposedly frozen for eons in the deep cold of interstellar space? The Hubble Space Telescope, in the first half of October 2025, trained its formidable gaze upon the interstellar visitor known as 3I Atlas. For a period of 7 days, it performed a function not unlike that of a physician monitoring a patient's vital signs, its ultraviolet and visible light spectrometers, taking the pulse of a most critical lifeblood. Water. The data stream revealed a startling rhythm, a surge in the comet's outgassing that culminated in a peak water ejection rate of 1.2 kilograms every second. This was not a steady, predictable flow, but a pulsing, almost physiological event. What internal clock, what hidden cardiac muscle, could dictate such a precise and powerful rhythm in a body of ice and dust drifting through the void? According to current models of cometary physics, such outbursts are typically attributed to the simple, relentless mechanics of solar heating. As a comet arcs toward the inner solar system, volatile ices locked within its nucleus are subjected to increasing temperatures, sublimating directly from solid to gas, carving channels and rupturing the fragile crust. The observed peak could be explained by a specific region of highly volatile ice rotating into direct sunlight, its transformation violent and immediate. The energy budget provided by our Sun would, in this conventional view, be entirely sufficient to power such a hydrological event. Yet, the clockwork precision of the event, its defined onset and peak across several days, gives one pause. Does the simple, passive process of heating fully account for the complex, almost metabolic behavior we are witnessing? This leads us to a more speculative hypothesis. Perhaps we are not observing a simple melting ice ball, but a body with a complex internal structure. The cyclical nature of the water ejection suggests a system of pressurized, subsurface aquifers, sealed beneath a non-volatile crust. The thermal wave from the Sun, penetrating this crust, could create a regular cycle of pressure buildup and release, a true hydrological heart beating within the comet. The water, superheated and seeking escape, would then pulse through fissures and vents, in a rhythm dictated by its own internal thermodynamics. But what if this heartbeat was not entirely self-generated? Could an external stimulus have triggered this event? Prior to this outburst, 3I Atlas passed through the gravitational and magnetic sphere of influence of Mars. Is it conceivable that the subtle tidal forces or interactions with the Martian magnetosphere acted as a key, unlocking a previously sealed subterranean conduit, opening a main artery for this torrent of water to follow? The empirical evidence gathered by Hubble is unequivocal. Its ultraviolet and the visible light spectra show a definitive fourfold increase in the column density of water vapor after the 10th of October. This was not a minor fluctuation, but a fundamental shift in the object's state of being. Furthermore, the non-gravitational forces acting upon the comet, those subtle nudges that alter its trajectory beyond the pull of gravity alone, were updated in dynamical models. These new beta forces were found to correlate precisely with the magnitude and direction of the water jet, confirming that this outflow was the engine pushing the comet ever so slightly off its predicted course. Corroborating data from the Stratospheric Observatory for Infrared Astronomy, captured in its final operational days before retirement, detected a similarly powerful surge in the hydroxyl radical emission at 308 nanometers, a known and reliable proxy for water dissociation in space. The chain of evidence is robust and consistent across multiple instruments and wavelengths. Yet, does this wealth of data bring us closer to understanding the cause, or does it merely deepen the mystery of the effect? Our analysis must therefore proceed through escalating tiers of complexity. At the first level, the explanation remains rooted in stellar thermodynamics. The heat of the sun is the primary, and perhaps only, catalyst required. The comet is a passive recipient of energy, and its reactions, while dramatic, are fundamentally simple. This is the most conservative and scientifically parsimonious view. But then we must ascend to a second level of interpretation. What if the comet's rotation itself plays a more active role? The geometry of the jet suggests it was not isotropic, but directional. Could a resonance between the comet's spin and the thermal penetration depth create an amplification effect, focusing the outgassing into a narrow, powerful nozzle? This would transform the entire nucleus into a crude, natural thruster, its rotational kinetic energy, harnessed to accelerate its own material into space. Is the universe, then, replete with such unintentional engines, their silent firings altering paths over eons? This invites a third, and far more profound, level of speculation. The ejected water vapor, streaming into the vacuum at high velocity, would itself become a medium for further complexity. As the water molecules are broken apart by solar radiation, they form a plasma, a cloud of charged particles enveloping the comet. This plasma sheath, this thin, self-generated shield, would then become susceptible to the influence of magnetic fields threading the interstellar medium. The water jet, initially a simple geyser, becomes an electrically conductive circuit. Could the comet be interacting with the galaxy's magnetic fabric in ways we have scarcely begun to model? Is the faint, flickering glow of its coma not just reflected light, but the signature of a fundamental electromagnetic interaction between a wandering body and the field lines of the cosmos itself? The implications of such a phenomenon are staggering. If this water jet is not a random eruption but a controlled, pulsed event, governed by the object's intrinsic oscillations, then we are witnessing a form of natural engineering on a cosmic scale. The mechanics of this system, once decoded, could provide a blueprint for a new class of propulsion technology. Imagine a spacecraft that does not carry its own volatile propellants in heavy tanks, but instead harnesses a naturally occurring water source from an asteroid or comet, using precisely timed energy pulses to generate a clean, efficient plasma thrust. This would be a green engine for deep space, turning the resources of the void into the very fuel for our exploration. But to what end has nature perfected this mechanism? Is it merely a chaotic byproduct of ice meeting light, or could it be a rudimentary form of propulsion used by other, far older travelers? The sheer scale of this discovery, the tantalizing possibility of a natural plasma thruster inevitably spills beyond the confines of academic journals and into the public consciousness, where the line between rigorous inquiry and boundless speculation grows perilously thin. As the whispers of gravitational anomalies and directed outgassing begin to circulate through unofficial channels, the need for a clear, authoritative voice becomes paramount. How will the scientific establishment, embodied by its great space agencies, respond to this burgeoning narrative, and what guidance will they offer to the millions of citizen scientists now turning their eyes and their telescopes to the heavens?